tonight's speaker is Dr. Willie Yee. He is an amateur astronomer and past president of the MHAA, member of the board of directors also. He's presently a solar system ambassador. That's a program. Solar System Ambassadors is a program that's supported by NASA and the Jet Propulsion Laboratory in Pasadena, California. Dr. Yee is also a retired psychiatrist and a magician. As a magician, he was trained at the world-renowned McBride Magic and Mystery School in Las Vegas. Dr. Yee has been a Red Cross volunteer for 13 years, active in sheltering, mental health, community relations, and teaching. Dr. Yee's presentation for tonight is titled, "What Have Space Telescopes Told Us About the Universe?" Specifically, he will discuss the findings of the Hubble and Webb space telescopes and what they have taught us about the history of the universe and how they are changing our current theories about its evolution. With that, let's give a warm welcome to Dr. Yee.
Okay, while we're doing this, I want to say something about the Solar System Ambassador Program. JPL just had another huge round of layoffs, including 3 out of the 4 staff of the Solar System Ambassadors Program. So now we have one person running the whole thing. She says it's going to continue, although she's going to have to do the work of 4 people, and hopefully some volunteers will step in. But she said that the program will continue, but it's a scary time. There we go.
Is that going out?
Yes. Okay, so I did get a little help from Chat GPT, which I recommend you try. Basically, I just asked this question and it gave me a whole outline. But I did check everything that it told me with original sources, mainly NASA. The Solar System Ambassador Program is volunteers. We do. There is a support staff at JPL, and we get support in terms of educational stuff, briefings, goodies to give out, some scheduling help, and things like that. That being said, my views do not represent that of NASA or JPL. So I want to talk about our 2 great telescopes. I think my next talk, I'm going to talk about all the others because they don't get much coverage. So I'll start with the Hubble telescope. Why do we need a space telescope? Well, the first issue back when it was conceived was to overcome the blurring of the atmosphere. That's become less of a problem in recent decades because now we have artificial stars and adaptive optics. So our ground-based telescopes have increased their resolution from this to this. We can now get from ground-based telescopes. You still get better from space.
They can't see that online.
Oh, they can't see my arrow. Oh.
The mouse, I think they can see what you're pointing at.
All right. Well, maybe not. All right. So the other reason to have a space telescope is we can see frequencies that are blocked by the atmosphere. If we look at this little diagram, we can see that a whole bunch of stuff in the ultraviolet gets screened out, which is good. Otherwise, we'd all bake and sunburn instantly. We got our visible light, and then moving to the right, we have gaps in the infrared, and then there's a big gap in radio telescopes. So there's no reason to have a radio telescope in space. But a lot of information is in that infrared piece and in the ultraviolet and down into gamma rays, which we need space telescopes to see for. Also, no light pollution in space. The space telescope was first suggested in 1923 by Hermann Oberth. Lyman Spitzer made a first practical proposal of what one might look like and how to get it up there. And it was in 1959 that Nancy Grace Stroman was put in charge of NASA's observational program, And she was the one who said, you know, we're supporting all these ground-based telescopes, but it's time to go into space. And she really got Hubble kick-started. So who was Hubble? Most of us know that he was the one that showed us that the universe was more than the Milky Way, that all these fuzzy things out there were in fact galaxies. And then furthermore, all these galaxies were moving away from us, that the universe was in fact expanding. So it was very appropriate because this is one of Hubble's main areas of research. This is part of a Great Telescopes program, which also included the Spitzer, the Chandra, and the Compton. So maybe that's my next talk. We don't hear much about Compton. It only operated, it's in the blue line there, for 13 years, and that was a gamma ray observatory. The Hubble is now going, it's going to be celebrating 35 years this year. It was originally intended to last 3 to 5 maybe, and it's still cranking along. Chandra is still working. Spitzer was decommissioned in 2020 on its last trip around the sun. So we don't have we did not have at that point a good infrared telescope. So what do we see when we look in these other frequencies? This is the same object. In the middle is what we see in our visible light. On the left is what Chandra sees in X-ray, and on the other side is what the Spitzer sees in infrared. So we get radically different views of the same object if we can look at in different frequencies. And we can combine some of those. So if we take the Hubble in blue and Spitzer in red, and Chandra, and I think they put it in green or whatever, these images can be combined, make really pretty pictures, among other things, as well as what they reveal scientifically. Hubble had 13 instruments on it, only 14 at a time, only 4 at a time. But over, it's been around 35 years. There's been several service missions because it was launched by the space shuttle. That determined its size. It had to be big enough to fit in, had to be small enough to fit in the space shuttle. And that the Hubble and the space shuttle were actually designed pretty much together, and so there's 2 teams. How big do you want it? How big can you give us? And how big can you get into orbit? And it was the most expensive NASA science project ever funded. Was it worth it? Well, it generated over 21,000 scientific papers. So y'all gonna be here a while tonight. So what did we discover? First, it measured the expansion of the universe. We did not have a good idea of what it was. Our original estimates were off by a factor of 2. Its measurements were accurate enough that not only did we measure the expansion, we also measured the fact that it's accelerating. So if you throw a ball up into the air, it goes up, it comes down, gravity pulls it down. Everything in the universe is getting thrown out, and gravity should eventually pull it back out. There's something else pushing it. We call it dark energy. So we also have this stuff called doesn't matter, which has no effect on the universe whatsoever. Hubble was also able to measure the age of the universe. Don't forget, some people here are under 35 have known since you grew up how old the universe was. When I grew up, nobody had any idea, and there were estimates all over the place. And Hubble was initially able to narrow it down between 9 and 14 billion years. So additional measurements and additional scientific instruments have now narrowed it down to plus or minus, 20 billion years, 20 million years. So 13.8 billion years is our best guess at this point. Hubble was also able to begin to investigate the reionization phase of the universe. What is that? Well, after the Big Bang, stuff started eventually coalescing into matter, mostly hydrogen atoms. So,
In a dispute calling it reionization. It's the decoupling, I think, but there was no ionization, so it's not reionizing. I've heard that before.
well, there may have been an instant when the electrons were created before they actually got into orbit. So once they got into orbit around a proton, then it was no longer an ion. So during that period, there was no light being generated. There's nothing to see because each electron was attached to a proton, and it's only when it changes state, it changes its orbit, that it puts out photons that we can see.
Oh. Wait, I'm mistaken. This is a reionization, not after decoupling.
Yeah.
Okay.
Okay.
Never
So.
mind. Sorry.
So eventually, what was it that actually kicked enough electrons off of their protons to create photons? And that apparently was the beginning of the first stars. So the stars made enough energy to start moving things around, and now radiation started coming out that we could now see and observe and measure. So there was that whole field. Then there were the Hubble deep fields. The deep fields were a project of the director. The director managed, one of his perks is I get 10% of the time to do whatever I want. And I don't have to go through this friggin' committee where 4 billion scientists are trying to get telescope time. I get my own time on the telescope. So at some point he says, I want to point this telescope into a part of the sky at which we have never seen anything. As far as we know, it is empty, blank sky. But we have a more powerful telescope. Maybe we'll see something that we haven't seen before. A lot of people said, you're wasting your time. It's not going to find any new galaxies, but boom. Now, look at this picture. You see all these fuzzy things are galaxies, but everything there are no individual stars here. The smallest dot here is a galaxy. So there are thousands of galaxies in just this little picture. So immediately we went up, there's got to be at least 60 billion galaxies in the universe from that one shot. Later, as we get more data, we think, well, maybe there's 125 billion, maybe there's 2 trillion. So the latest evidence from the New Horizons telescope. I remember New Horizons, that was the one that went to Pluto. During some of its travel time, we pointed it out in space and counted some galaxies, and it says there are 200 billion galaxies in the universe. So there it was, and it's still doing science on its way out. Initially, they found a whole lot of bright stuff in the early universe, and they thought, these are brighter galaxies than we expect. And then later on, it was just, oh no, they've got black holes in them, and they're creating a lot of extra energy that we've seen maybe not so many galaxies. But we were able to measure the density of galaxies and their formation over time, down to about 400 to 800 million years after the Big Bang. It was a Hubble finding that most galaxies have supermassive black holes in their center. We didn't know this before. The size of the black hole seems to be correlated with the central mass of the central bulge. And we think there's some kind of relationship between the black holes and galaxy formation. And that is a big issue. Here's a blow up of one galaxy and its supermassive black hole and some of the effects that it's creating. So this is all, again, from the deep field. we also know there's a black hole because we can see radiation approaching and going away from us in the same area. So the radiation that comes close to us is being blue shifted because the stuff's coming toward us. That which is going away from us gets red shifted. This is the same stuff, so it means this thing's going around its center. We're also able to measure star formation and life cycles. The famous pillars of creation, these clouds of dust in which new stars and protostars are being formed. Hubble did have some infrared capability in some of the instruments. So looking at that pillars in infrared, we could see a lot of the stars inside it and behind it. And you look at the whole background here up in the upper right and left-hand corners, it's all obscured by dust. Infrared can see right through that to the stars behind it. Before the Hubble telescope, this was the Crab Nebula. That was as best as we could get. With the Hubble telescope, we get that. So there's a lot of science that can come out of that. Hubble has also been able to examine exoplanet atmospheres. So by watching planets as they transit their star, we have the spectrum of the star. We see the planet go across. We see changes in the spectrum, which means whatever light from the stars going through the atmosphere of the planet can be analyzed. And so we found an atmosphere in 2001. It was sodium, ionized sodium. Water was detected in 2019. It was a rocky planet in the habitable zone. So again, a possible place to look for life. 2003 found a hot Jupiter that's evaporating. So it's close enough to its star that its atmosphere is getting blown out into space. But what its eventual fate is, I don't know. That's lots of planetary science there. So now we do the James Webb Space Telescope. I'm not going to go into the technology of that thing, but it is just one of the most awesome technological things that's ever been done. Just to unpack this origami thing was 120 some mission critical steps. There were 120 things that could have gone wrong, that could have turned this thing into space junk, and it all worked. It was behind schedule and over budget, way over budget, but it works. It can see through the dust. It's an infrared telescope and doesn't do anything in visible light. So everybody thought, oh, we're not going to get any pictures that we can see. Well, we can translate those pictures. I mean, they come out gray, and then we put. There's one person in NASA whose job is to put colors into these space pictures. So a much bigger mirror, 100 times powerful, is more powerful than Hubble's. So you can see Hubble's mirror is smaller than that black hole there, and each segment of that is all of the Webb is almost that big. So it's got 100 times light gathering power of the space of Hubble. It was named for James Webb, who was the second NASA administrator. We had help with this from the European Space Agency and Canadian Space Agency. And it was the European Space Agency that actually launched it aboard an Ariane rocket. We had to take it down to South America. Was it French Guiana is where their launch site is. And so now it's orbiting at Lagrange point 2, which is on the other side of the moon's orbit. That is a stable place where the gravity of the Earth and the sun balance each other out. And so if you put something there, it's fairly easy to keep there. And Webb actually orbits that actual point. And it's very stable, so that as the Earth is going around the sun, just couple 100,000 miles out, Webb is also going around. One of the technological breakthroughs was there was only supposed to be enough fuel for 2 to 3 years because it needs to be reoriented and adjusted in its orbit. They inserted it in its orbit so precisely, they now estimate that fuel is going to last 10 years. Something else may break, but who knows? So what have we discovered? Well, we looked at the universe in the first galaxy. Hubble was able to go back to 400 million years. Webb went back to about 250 million years after the Big Bang. More galaxies, more luminous, and more numerous than expected. Black holes, 10 to 100 times more abundant than expected. And questions about the standard cosmological model have been raised. Here's one way to think about it. It's probably wrong, but it gives you an idea about how to think. I used to think the way a galaxy formed was dust formed into lumps, and smaller lumps made bigger lumps. Eventually you got stars. Eventually some of them got big enough to turn into black holes. Eventually some black holes got big enough and merged and became a supermassive black hole at the beginning of the galaxy. That may be entirely wrong. It's possible that the black hole came first. It may be a piece of the original universe that broke off or formed very, very early and is the basis for our galaxies forming and taking the shape that they do. Probably wrong, but this is the way we now have to think about this. So we're able to formulate star formation in dusty regions. Again, here's Hubble, and then here's Webb's infrared image. Look at the number of stars in the background. It's amazing what a bigger telescope can do. Examining the actual dusty regions, we find heavier elements that we didn't know were going to be there, and these are eventually becoming the building blocks of stars and planets. So it means something else went on earlier in the previous cycles of star formation and turning into dust that created this. Again, we were able to examine exoplanet atmospheres. 55 Cancri E. I don't know if you can see 55 Cancri with a regular telescope. I guess you can because it's on a star chart if they've got a number on it, big enough ground telescope. Number E is a hot rocky planet. Is the first one with an atmosphere that is either carbon monoxide or carbon dioxide. So this is what the scientists look at when they look at Hubble. They don't look at these pictures. They look at graphs. The blue and red lines are predicted lines. These are models of what the atmosphere of 55 Cancri E would be. If it was basically a dusty planet with just dirt and maybe vaporized rock, you would get that red line. If there is in fact a volatile atmosphere, carbon dioxide, carbon monoxide, and stuff like that, you'd get the blue line. The yellow dots are what Webb found with one camera, and the purple dots are what it found with the mid-infrared camera. So we can see you got a pretty good close match. There's an atmosphere there, and it's made of volatile chemicals. There was another planet called WASP 107b, and it was a very puffy planet. It's not quite a Jupiter, but a smaller planet with a lot of fuzz around it. The spectroscopy looked at the chemistry, and it indicates that basically this atmosphere is getting tossed around by the elliptical orbit of the planet. When it gets close to its star, it goes one way. When it goes another way, it unionizes and changes around and changes shape and in all kind of weird ways. So, but we're able to, with Webb, look at a planet's atmosphere that closely. Here is, again, it's a transmission spectrum. They had to redo this graph because you see that big hump right there at the beginning of the purple? They didn't expect that because they didn't have sulfur dioxide in their model. So they had to go back and redo the model to include the possibility of sulfur dioxide and get a match with what we were seeing. The turquoise green stuff at the other end, that's a Hubble observation. So now we're getting these telescopes to work together, each one contributing in its own strong point. So we hope Hubble keeps going. Hubble has been pronounced dead or near dead several times. It's got 4 reaction wheels, basically gyroscopes that stabilize it. 3 of them are dead. They didn't even think they could point it accurately with only 1. And they've done more engineering workarounds, and it's still trucking along there with only 1 wheel. When that goes, it's going to be tumbling around at random. Galactic evolution, we can look at things like Stephan's quintet. You can see that with a regular telescope if you've got a big enough one. So we can see these long tails, and this is the effect of the interaction of these galaxies and the black holes that are in them. So there's quite a bit of detail that Webb can discover looking at these galaxies. We think that there might be tight groups for this throughout the universe. When these tails get triggered, dust gets scattered all over the place and reformulated, and perhaps colliding with stuff from other galaxies and possibly being the basis of forming new stars. We also look at planetary formation. Here is a evolving star. It's got massive outflows, but if you look right in the very center in that white area, there's a little black line across there. That is the protoplanetary disk. That is basically a rotating disk of gas that's eventually going to become the stars and planets of that system. Rolf Rayet, they looked at this thing for the first time. The scientists look at that. This is an artifact. Turns out it is not. This is a result of periodic events happening in this star. I think every 18 years, it blows off a shell of gas with great regularity, moving out at a very even speed. And so we got all these shells of gas moving through space over time. Black holes and active galactic nuclei have been studied. We can see the emission from the dust that goes around them, not only stars. It doesn't have to just eat stars to make visible radiation. We think that there's some superheated dust gets fueled by these black holes. Although we found more black holes than we expected, we found less active galactic nuclei in the early universe. We've also found that there are these shocks from black holes. Every once in a while, they just shoot out big bursts of energy that also heat up the dust. Again, heated dust gives off infrared radiation that we can see and measure. Here is ESO 428, and these spikes are not telescopic artifacts. Some of them are actually jets coming out of this. I think it's a protostar. So what have we found out? Putting it all together. The universe was more active and earlier than we expected. Stars and galaxies were forming at a faster rate than previously thought. The transition from the dark ages, when there was no light, to the epoch of ionization has been studied in some detail. And again, that's changing our model of how the universe must have expanded. The galaxies in the early universe were very diverse, unexpected diversity in size, structure, and brightness. Some appear more developed than the theory predicts. So the theory is in deep trouble. Which assumes that there was cold dark matter and our regular matter, and that's basically what created the universe. Trouble is that cannot account for how early these galaxies were forming. So something else is going on. So the whole model of how the universe evolved has got to be redone. Still in progress. Breaking news. This circulated on our own emails a while ago. This was in some journal that I called Brighter News. The universe is significantly older than previously thought. I tracked this down. There's an original paper by R.P. Gupta at the University of Ottawa. And he suggested that the universe is in fact 26 billion years old. He's not on the Hubble team. The article gives that kind of impression that these are Hubble scientists. The Hubble data is available to anybody. You know, you know enough data hacking and stuff to go through it. You can get all these pictures, all this data, do whatever you find. So there's plenty of work for graduate students to do. And he's taking the data from Hubble that, as we know, the early galaxies were not as we had predicted them. He added a formulation that had been abandoned a while ago. It was called tired light. That not only does light get stretched out as it's moving at higher speeds, as it goes through more and more and more of the universe, it gets a little wobbly, it gets tired. So they called it tired light. That something was happening to the light as it went through these vast distances of more or less empty space, that was changing it so that what we're seeing is not what we think we're seeing. And so he did all the math from that model and put it in. So this paper is really heavy on math. The number you need to see is on the right-hand side. That's the 44th equation, and that's only in the middle of the paper. And he did all that. The trouble is, it doesn't address all the other ways we have of measuring the aging of the universe. So it's using a model that is still highly questionable. However, if it turns out to be truth, you heard it here first. All right, bonus. We can turn the telescope to the solar system. Jupiter. On the left side is in regular light, on the right is in infrared, and you can see auroras on Jupiter with the Webb telescope. Uranus, its rings are too faint to be seen most of the time, but with this Jargundus mirror and no atmosphere and infrared, we can see it, and you can see several of the moons of Uranus in this picture. Neptune, we can see its rings too, and stuff happening on the surface, plus a bunch of its moons. Here's it all traced out over time. You can see Triton in the lower left-hand corner. You can see this was a timed exposure, so all the moons are smeared out into lines. Small bodies, even Dimorphos, the asteroid that we redirected. That thing has changed its orbit, which was what we hoped, and it's changed not only because we smacked it real hard, but it also turned it into an active asteroid. So it's basically a comet shooting out stuff from it, and that's additionally changing its orbit. So this is the first observation that was ever made of a asteroid being turned into what we call an active asteroid. An active asteroid is basically one that has comet features, but it is not in a cometary orbit, it's in an asteroid orbit. Okay, any questions?
Okay, can you hear me? I can be heard?
I can hear you.
All right, that's good. So these primordial active galactic nuclei, their redshifts, I assume, as measured by the Webb, are same as we would expect.
Yes, they are as far back as we would expect.
But
We didn't expect to see things that far out,
yeah,
which means that early in the universe.
and as many, correct?
Right.
Yeah. So so this tired light idea, is that saying that the light coming from those early nuclei,
Yeah.
makes it look like it's going at the redshift that we see,
Yeah.
but it's actually should be greater than what we see?
Right.
Okay, that's, and the other possibility is that the galaxies form a lot faster than we thought.
Yeah.
You know why? Never mind.
No, that's that's what the science is all about. There's another 21,000 papers to be written.
Would that, I get a follow up? Okay.
Yeah, I mean, all this
Oh,
stuff raises
okay.
as many questions as it answers,
Yeah.
of course.
Does this relate at all to the phenomenon whereby the universe is accelerating? Would these AGNs be acting as gravitationally to be pulling things faster than we expected?
Who knows?
Okay.
Well, but again, and how that depends on what's the nature of dark energy. We don't know enough about dark energy to be able to say how that's all interacting and what's
Maybe that is
stretching everything out.
Okay, I'm done. There you go.
Not a question, just a comment. I just noticed that tomorrow is Edwin Hubble's birthday.
Eh,
Any more questions in the room? Oh, we go.
I just hold it like this.
Yes.
Okay. So this past week, the New York Times had an article about the James Webb telescope that was observing the Orion Nebula. And I guess there's something called jumbos. Do you know anything about that?
jumbos.
Yeah. They're like paired objects that are being broken off of something.
Oh, there's something vaguely rattling around in my head about that, but I don't remember what it was.
Okay, no worries, no worries.
Anyone else in the room? Oh, yep.
Thank you. I'm curious with some of the new stuff that the James Webb can do that we couldn't do before. Is there anything that, like any light that we can expect to shed on some known issues, or put a different way? Like, what do we know that we don't know that we think that the James Webb could help with? Just
What do-
curious.
What do we know now that we didn't know before?
Or what do we know, like, what do we know that we don't know now that we think like the James Webb could help us with?
Has it defined what we don't know? Yeah, we don't know what happened in the early universe. We don't have a good explanation for how we went from ions and dust and gas to galaxies with black holes and galactic nuclei. What went on? What the intermediate steps of that are, we don't know. Where did those black holes come from? Maybe they did form the way I said from other black holes and stuff, but at some faster or some invisible time and rate.
Yeah, as a follow-up to that, I think one of the things it's doing is that it's, as far as exoplanets, in other words, when an exoplanet transits in front of its star, we're getting a lot more detail as to what is in that planet's atmosphere than we ever had before, and that's one of the things that's starting to materialize.
Yeah, and the whole science of exoplanets has totally turned on its head our theories about how planets are formed, because our initial theories are only formed from our own solar system. We only had one example of a solar system, and it turns out we're kind of freakish. We're a very unusual solar system, so it's all being stood on its head.
What do we know about stars going around these AGNs? And do we think there are stars there, or can they be detected?
Oh, we could see, in fact, that's how we discovered the black hole in the middle of our galaxy. There were stars in elliptical orbits going around very fast, something very big.
Right.
We could calculate its gravity.
Yep.
And we couldn't see it.
So those are assumed to be stars that are going into the AGN, or
they're orbiting
or is it just
orbiting it? Some of them may be on decaying orbits and will eventually
it's not
get
just
eaten.
gas and dust, it's actual stars.
The actual stars, yeah.
Okay. I'm done again.
I had some interesting imagery of that.
So the scenario of Interstellar, the movie, is not impossible. Some of it's impossible. Yeah.
That was probably accurate. Yeah. I remember seeing an article not too long ago about being able to see the surface of another star for the first time. Some details on the surface. Do you remember if that was from Webb or was that a different scope?
I
Teresa?
don't remember seeing that. I think they can characterize the surfaces, but whether it's been rocky or, whether it's rocky or not.
Yeah, they were showing like
And
they were showing
maybe
that they had like
whether
sunspots.
it's all water.
It saw sunspots or something. It kind of. That was the Teresa one. Chorizo?
Yeah.
Oh, there was that. Yeah, no. Yeah, I remember that. The fake one. Yeah, no, there was a real article about that though. They actually resolved some kind of darknesses on there that they believe are sunspots on a different sun.
I don't know, I'll have to check that out.
Okay. Yeah.
Anyone else in the room? Anyone on the Zoom session have any questions for Willie? No? Hearing none? We're out of questions? Thank you, sir.
Okay.
Absolutely wonderful.